What's up, my fellow children of God? How's it going? I know God loves us. We have an experiment here I was going to show you. It's kind of far away, so I'm going to bring the camera in closer. There on the left is our little heater. Inside the heater is a submersible pump. This is a external finned heat exchanger. They use these to cool transmission fluid for trucks when they're pulling and the friction load gets pretty heavy and it heats up. Here's our DAC unit that collects our data, and I'll just trace the fluid flow for you. So out of the heater, or the heated tank, our reservoir here, it comes around this tube, then goes through and it measures the temperature right there. Then the pressure is measured and transmitted. That's a little pressure sensor. And then there's a needle valve. Here you can see it where you can control the amount of flow by closing or opening that valve there. And then the flow comes here through this flow meter and then back and enters the exchanger. It's a little finned exchanger. And then the flow exits. And then the temperature is measured on the exit, and then it flows back into our reservoir. This over here is our National Instruments data acquisition unit. Has a little 12 or 24 volt power supply. This module here, that guy there is measuring our two temperatures, and it's measuring the voltage. So this, let me zoom in there. That yellow is the positive and red is the negative, and in ports 4 and 5. And there's the second temperature measurement. And then here is our flow signal. So there's a positive, which is the yellow, and white's the neutral. And it's going, that wire is going around in my hand over to our flow measurement device. There's also this power line that's plugged in here. So that's measuring a voltage, similar to the thermocouples measuring temperature here. Here's measuring flow of voltage. Thermocouples also measure voltage, and they're wired similarly as the flow. This is where the pressure is being measured, and it's measuring the current. And in this particular setup, the pressure sensor has two leads, so simply a positive and negative, and so it's being powered. At the same time, it's using those same two wires to allow a signal through there. So what happens is it powers it, and then in a loop kind of a manner, you measure the current. So you wire it in series with the data collection, and this data collection port is measuring the current. So if I were to trace it in a loop, they call it a loop measurement. So here is the power, this red. It's powering the device. Positive from the power supply is powering the device, goes in there and then comes back out. Then it's connected. These two wires are connected. I'm not sure you can see that very well. Here's the positive going to the positive power supply. Here's the negative, and these two ports are connected on the back here, so it's as if they're in the same port. Then this wire comes here into the positive supply for the data acquisition. Then the negative is going back into our negative power supply here. Power to the pressure sensor to the data acquisition. So it's one series loop. Here's the data that we're collecting right here. So yeah, you see that there's a temperature change of about 1 degree right now at a flow of 400 milliliters per minute, and the pressure is around 2.3 psi. And you can see Q, that's the amount of watts it's being lost from the water through the heat exchanger. So I'm going to change the flow. What I'm going to do is I'm going to decrease the flow with this little valve here, little needle valve will reduce the flow, and we're going to see what's going to happen to our temperature change. What do you think is going to happen if we decrease the flow? Let's try it. So I'll start changing that. You can see our flow will go down a bit. We'll try to cut it in half approximately. Around 200. There it is. So we're going to watch to see how the temperature change is affected. You can see our pressure went up slightly, and you'll notice what happened to our heat flux. So our temperature change is going up, and our heat flux, Q, went down. Now we're going to turn the fan on and see what happens. Let that stabilize here just a second. Went up 10 or 20%. Let's turn the fan on. So our heat flux is increasing with the fan on, and you should see our temperature change across the heat flux also increases. This is the second attempt of filming this. The first time it took me 11 minutes to go through, so I'm going to try to go through it in a little bit quicker. So the burden is on you to review it. It's on the GitHub repository, but the intent of this sheet is to predict the temperature drop through the heat exchanger with different flow rates and inlet temperatures, as well as different flow rates of the air across in parallel flow to the heat exchanger. So once we've got a model like that, then we're going to use it to predict what we'd get from a vehicle if it were, and the fluid changed to automatic transmission fluid. And that's at the bottom of the sheet. So in interest of time, you can see these equations. Those are standard equations. And I will say quickly, it's best if you can create a class where your material properties are defined, and then you can define water properties and automatic transmission fluid properties, and then you can make your functions inclusive of a substance or a fluid, and then swap that out easily instead of having to recalculate everything by changing the properties up above the sheet, in the sheet. You'll have to define, of course, the heat exchanger properties as well. Those are there. Here's the equation you'll have to solve for both the rough and the narrowed-in model. The rough model is assuming a constant overall heat transfer coefficient that you can find in the NCES handbook for finned heat exchangers with water and air, and it gives this range 25 to 60. We've used just 60, and you can see doing that you get this kind of an effect with the flow, as well as for the temperature difference through the heat exchanger as a function of flow for the different inlet temperatures. Of course, as you get higher temperatures, you're going to get higher temperature differences as the heat can dissipate, and there's a greater driving force. Here is the plot for the heat exchange. So even though there's a larger temperature difference at a low flow rate, that means a lower heat exchange amount as the
heat transfer is not as efficient with lower flow. Here is now definitions of the narrowed in model, where we have our external heat transfer coefficient and our internal heat transfer coefficient, so it's not just a constant. And I've included in these, just quickly, that in order to match the experiments, I've had to increase the Nusselt numbers, or the estimates, by about 50% or more. I'll let you think through that, but here is our predictions with the narrowed in model. In this case, it's including the airflow as well, external to the heat exchanger. And then here's our experimental data that you saw the setup earlier in the video. And here is our results for how the model agrees with the experimental data. You can see it does a pretty good job. The X's are the the model, and the circles, dots, are the experiment. And this is with and without airflow for different incoming or inlet temperatures. We calculate the squared errors for each of those points. You can see for the narrowed in model, it does a pretty good job. Not so much for the rough, where you're assuming constant and a lower heat transfer coefficient, overall heat transfer coefficient. Now we're going to apply it to a transmission oil cooler. So for our predicted outlet temperatures, we've got this substance and we've changed it from water to automatic transmission fluid. And we've set up kind of a mock, or just a fictitious temperature rise under duress for the transmission, where without the heat exchanger, the temperature is this profile, where it gets to 110 degrees C approximately. But with the heat exchanger present at a 0.5 liter per minute flow or a 2 liter per minute flow rate, you can see that the temperature is reduced by approximately 4 to 7 degrees. And yes, that can prevent damage to your transmission. This is the model here that we've used for the lab is one of the smaller heat exchangers, but this is an estimate of what could occur, but of course is dependent on the flow rate and other conditions that may not have been adequately included here, but it is an estimate. Thank you so much.